Welcome to Friday afternoon lecture series, right? The last of the bunch. So the first thing I want to do is just clarify that the initial invite mentioned I-35W and I-74, and for all those that turned in to learn a lot about I-74, I apologize, and to our client, Iowa DOT, and the Benish team, there was no intent to share a lot of information about I-74. So other than some general references here or there, we won't be talking about I-74 in any particular detail today. For 35W, I think many of you in the room are familiar with this project. It started with the bridge collapse back in a number of years ago. And with the reconstruction, it was a very aggressive design, build, reconstruct. And there were a number of basic ITS elements that they wanted put back into the system. Reestablish the communications infrastructure, reestablish the CCTVs that were along the corridor, and reconnect a number of existing DMS and traffic monitoring stations. But what we want to spend a little bit of time talking about today are the unique elements in the project. We did some forward-looking infrared cameras for bridge security, some other bridge security devices, the anti-icing system that was incorporated into the structure, smart bridge system, and that name's evolved already into bridge health monitoring. And then there's some aesthetic lighting, IP addressable downlighting that were all incorporated into the project and was wrapped back through the communications with the Minnesota Department of Transportation. So there's the location of the bridge after it fell into the Mississippi River, a major connector along between the Twin Cities, between Minneapolis and St. Paul. The project went from, it was initially described as a project, a design build on steroids, a very aggressive schedule. Approximately $190 to $200 million of reconstruction of this bridge and 2 interchanges on either side of it. And the concept, we showed up to start looking at the ITS design around Thanksgiving, and they wanted it done in January. And so it was a very aggressive time frame. There are a number of rapid changes. Do I need to do something there? No. Okay. The number of rapid changes in the project. Initially, all the conduits for the ITS communication and power were going to be included in the outside barrier rail. And shortly into the project, they said they want an open barrier rail on the project so that you could view the skyline and so forth. So they went with an open barrier rail. Now we had to find a new location for all the ITS conduits crossing the structure. And because Minnesota is the land of 10,000 lakes, they didn't have enough of them, so they wanted to build 2 architectural ponds on the project. There's a pedestrian underpass that needed to be dealt with on the job. And then in the urban environment, the right-of-way is so limited that we were forced to look at unique ways to route conduit around the project. So the concept was pretty aggressive. They initially had 48 fiber on both structures. They wanted to come back and put a trunk line back across both structures, 48 on the west side bridge and 96 on the east side. You can see how tight the dark lines represent the ITS conduits, and you can see how tight they were to the corridor. There's a pond right up here that caused us to reroute conduits and so forth. And from a design standpoint, this is something that you've dealt with traffic engineering, traffic signal designs, routing conduits around an intersection. It's just slightly more aggressive. And so where we went with the conduits, we were with the concrete box girder design of this bridge. We actually came inside of one of these box girders and had to come up with a number of different details to support these new conduits inside the box girder. The bridge itself has a deflection of 13 inches. So this 2,500 foot bridge is expected to move 13 inches through normal deflections. Additionally, the non-metallic conduits are expected to move anywhere from 2 to 4 inches every 100 feet due to thermal expansion. So we had to take all that into consideration, where our junction boxes were, where our cabinets were going to be to get up to the bridge health monitoring and other devices on the project. From a conduit routing standpoint, down each one of the piers, there were 4 conduits placed for communication and power. They wanted to measure loads on each pier during construction. And this is a typical detail of the hanging system inside the concrete box girder. Significant design allowed for the anti-icing, the bridge security, ITS communications, and then power for both ITS and for street lighting were routed inside the box girder. Once you're inside, you had to find a way to get to the outside of the structure in order to get to the devices. So we had to find the ideal location, working with the structural engineers to get a penetration through the outside of the box girder and then into the webbing for the pier, and then ultimately down the pier. So picture inside the box girder, shows the hatch that allows you to get up inside, shows some of the cabinets, not unlike you would put at a traffic signal or other ITS deployment. So the anti-icing system was also in the same concrete box girder. It had some of its own unique characteristics from a conduit routing standpoint, because although it's a pressurized system, the anti-icing also has to drain. They have to be able to drain the system, so they want it built on grade so it will drain, well, which meant that it would have to cross some of everything couldn't be parallel throughout the project. There had to be adjustments within the box girder. Additionally, Minnesota DOT wanted to put forward-looking infrared or FLIR cameras for bridge security. They worked pretty well. They actually used thermal detection to look at bridge security, hatch monitoring, and other critical infrastructure at this location. They have the ability to pass or track from one side to the other. So we have one on each bank, and based upon the thermal imaging of the cameras, it can pass from one to another. And it also tracks and recenters the image on those thermal images that it detects within the video range or camera range. There's a picture of the camera near the hatches. I think you can see the hatch locations here. They're monitoring that, and then also the abutment right there, which is also a security concern on this structure. And so this monitors all of that at the same time on each bank. A number of sensors were embedded. Actually, over 350 sensors were constructed in the bridge. The first group here are chloride or corrosion sensors. They're actually embedded in the deck, and they're wired to the deck, and they're measuring chloride levels and corrosion within the actual deck. There are a number of accelerometers placed on the bridge, and the structural engineers dictated us the best location for these. We had to bring the ITS communications to it to be able to pick them up. And linear potentiometers near each end of the structure. And then vibrating wire strain gauges with temperature control at a number of places on the bridge as well. In talking with the University of Minnesota, where this was all, the data is also passed back to them, they said one of the most beneficial pieces of data so far has been the temperature, because they've had so much concrete out there, and just watching that temperature information as it cures and over the last 2 years has been relevant data to them. But they get thousands of bytes of data off of this structure. Before they opened the bridge, they actually did a truck loading calibration, and they actually brought a number of semis out there and parked them in different configurations and measured every one of the loads at different points and what each one of the sensors was reading. So they actually did a bridge calibration, which is unique within the industry. The first time I've had the opportunity to work on a project where they did calibrate the bridge beforehand. From a field integration standpoint, there are a number of things that we had to consider. When we first looked at the anti-icing for the project, Boshung had placed their pump house near the project site, and that's the large structure that you see in the image. Shortly thereafter, they came to us in the design standpoint and said, can we place a fiber distribution unit inside that pump house just to help make the connectivity? It's a secure location behind a fence. It would be a good place to put a fiber termination. And they said, sure, we can make that work. And it was about a week later, and we came back and said, oh, now we've got bridge security cameras, and can we route those through here as well? And then finally, the IP addressable lights, they wanted to have a control near the structure itself. And so finally, Boshung said, no, we don't want to redesign our pump house, and we don't want access, all those different access to that pump house. So what we did is we actually built a small little building. You can order these prefab buildings now, and that building was constructed to house all the ITS, bridge security, and IP addressable components that were needed. So not to race through this, but open it up to some questions here in a little bit. There's some real benefits of this type of technology. First, the real-time data from operations and maintenance, and be able to get that information out to the traveling public. Obviously the ITS components, which have been around for a while. The real-time data to the universities and to other research components is excellent. And then ultimately, finally, I guess I would say the cost is typically less than 2% on these large structures. So a large river bridge, I-74, the cost is less than 1% as you look at the overall project. So the benefit cost ratio is pretty significant. The amount of information that you get from this type of project relative to the overall cost is fantastic. So I probably raced through that a little bit after the start. I guess we'll open it up to questions if that's where we are.
All right, does anybody have any questions here or online?
Steve, does the system interact with the anti-icing system, the ITS technologies, and can you get the data on the usage of the anti-icing system?
The anti-icing system is integrated to the Minnesota Department of Transportation, and as the ITS elements as well. So yes, they can access the anti-icing controller and get the number of times that it's been deployed, pump level, and fluid levels on all the different, on the pump house. So.
Is there any other questions?
Steve, on the I guess they have weigh in motion detectors on the bridge, is that?
The bridge itself, in theory, it kind of acts like that because there's so many sensors on it.
Right.
They did not place weigh in motion on the structure itself.
I guess the question, are they using it for enforcement at all? Do they try and see if there's a heavier than normal load on that bridge?
They have not used it for enforcement to date. To date, it's been a research component to the University of Minnesota, and then the structural guys with Minnesota Department of Transportation. But it's not been used for enforcement.
So a question that I have is, the project of that magnitude is just unfathomable for me. how do you manage when you're working with that many different teams? You know, can you kind of talk about the process of, you know, when the de-icing system was proposed, how did that vetting process go? And, you know, how the communication within something with that, because as a graduate student, you're not exposed to something of that magnitude. Can you kind of elaborate on that process a little bit and talk about what that was like?
Sure. There were multiple, stakeholders for, use the Federal Highway System Engineering language. There are multiple stakeholders on the project and multiple members of the design team, and that's usually the case on a large project of this nature, and I-74 is no different. What it takes is a major effort to communicate between each design team. Bosheng, we had to move and adjust our conduits numerous times as Bosheng's devices for spraying the ramps were closer to the curb line, the shoulder, than where we wanted to have our conduits routed, so we had to move those again. So there's a number of iterations that take place as you layer on the different design elements. The IP addressable downlighting, for example, was another conduit that needed to make its way off the structure then, and to a point where it can be terminated and integrated into the system. So that they were a new user, because the city of Minneapolis ultimately controls those IP addressable downlights. So at that point, we had to look at switches and routers to be able to get city of Minneapolis into the system to control that as well.
And how was the public involved in that, the vetting process when you started the project? I mean, throughout it, there's many meetings, but how was the public informed of when the bridge is opening and the status and those kind of things?
With that project, because of the nature of how it fell, there was a significant public involvement component right from the very beginning. And each week, the primary contractor, FIG, would hold public meetings on site, and so they would basically do tours and walkthroughs every week with traveling with the public. So it was a significant public involvement effort.
Steve, you talked about bridge security. Can you elaborate a little bit what bridge security systems you really had in place and what threats you're trying to mitigate? I guess you have trap doors, but you're monitoring if somebody gets in those doors, but also if there's surveillance on top, so we don't have detonations of trucks and things like that.
There's a process that the Corps of Engineers uses to evaluate structures, and that is, I guess, a fairly secure process. They don't share a lot of that information, but they basically come out of those meetings and say, we want to be able to look at this, or we want to be able to monitor certain things. And so it was identified as critical was monitoring the hatch locations on the structure. And there are 8 hatch locations at each one of the concrete box girders to access that. And then they had someone with a background in being able to blow up structures provides input, and they determine what the threat level is from above the structure as well. Ultimately, it was determined that forward-looking infrared and then access hatch monitoring at each hatch, if the hatch is open. Not unlike a traffic signal cabinet. If you go to any traffic signal cabinet in Lincoln and you open the door, there'll be a notification that that door is open to the traffic maintenance system. And so a simple system like that can be integrated to every one of those hatches. And if anyone makes access to those hatches, it's not for maintenance purposes, it's integrated with the 911 security side of the city of Minneapolis and St. Paul. So.
There's a question from the University of Iowa. Is there any concern about the de-icing agent contributing to the degradation of the driving surface?
And yes, and that's the reason they put the chloride sensors in the structure where they did. And so they're going to monitor that. Now, the anti-icing systems over the years, they've they've looked at that. I think at airports they've had the amount of material used, or the percentage of chloride used on the system has caused them to have premature wear of the concrete. On roadway surfaces here, that I think that percentage is less, but they've studied that and they've come up with some different materials to apply. So my understanding is that they'll be monitoring it, but it's not as extreme as what they had a few years ago when they were using different materials.
Are there any other questions, either in the online audience or here at the University of Nebraska?
Stephen, just for a second, could you give us your thoughts on the future of these systems? I know this was a pretty special case in the way it was done, but where do you see this going with other bridges, both these sort of massive bridges, but also the ones we drive over every day, the smaller ones in the state DOT?
My opinion, having been involved with this a couple of times now, is that I think this is a growing area. The ability to integrate sensors into a structure is, I guess, becoming more, we have more details, we have the specifications, we have a greater level of understanding with that, and working with the structural engineers and the transportation management side of the house, we have found a way to integrate those two together fairly easily. It takes some work and takes some labor, but you can actually get a good wealth of data from there. I would see this as just a growing industry, and I'd also, we've been kicking around ideas of how could you have a series of temporary sensors that you could place on a structure and leave in place for 30 days and potentially integrate with your TMC to be the database that stores that data, and then move it over to the structural group for additional evaluation. So I see it as a growing industry.
Steve, early on in your presentation, you talked about the rails, and there was a new rail, and you could no longer have the conduit and utility lines there. I missed it, but where did you end up putting the roadway lighting system, and where's the wiring system that goes with that? I missed that on this new kind of bridge.
There's still a concrete barrier to the inside where they fix the light poles and so forth, and they come out of the cell to the interior. So they wanted the exterior rails open for viewability, but interior, the innermost rails were still concrete for placing the lighting.
Did you implement any different technologies to, mitigate scouring with this bridge?
That one, I would have to pass on to a number of other civils. If they did scouring, it was not a sensor that we integrated into, that I'm familiar with integrating into the design of the project. All of the sensors were placed on top or embedded in the structure above. For scour, they had brought power and communication down. I think that was temporary to measure the loads during construction. So I don't know that they had scour as a permanent measurement after the bridge was open.
I have another question online from the University of Iowa. And the question is, what happens when the sensors detect a lot of salt or one chemical or the other? And it says, is there a cleaner, or does the de-icer shut off? Or can you describe a little bit how those sensors kind of function?
Yes and no. We know where they're placed. We looked at the specs and how to tie into those. There's a data logger that basically pulls all that information. It's stored, I think, it was a minute interval. Now I think they're looking at 15-minute intervals or an hour. So they were getting a lot of data back to the University of Minnesota. Right now there's no real-time alarm notification system if they detected an unusually large percentage of chloride on those sensors. It would be a historic measurement at this point. But that's where I see the industry progressing to as well. You'd be able to have, if you can filter through massive amounts of data, and set an alarm on these, which is possible. You could have an alarm anytime a chloride sensor was beyond a certain threshold.
Are there any other questions, either in the online audience or here at the University of Nebraska? All right, well, I think this concludes our presentation. I'll hand it over to Dr. Ouellette to continue.
Well, thank you very much, Steve. Very
Sure.
informative presentation. I think for the students, I think we're just going to see more of this, as you're saying. A lot more sensors, a lot more ITS. We're used to thinking about it from a traffic perspective, but now it's getting into the infrastructure, and with the connected vehicle stuff that's coming down, it's only going to become more important. So it's always great to have alumni come back, and
Appreciate the opportunity.
we're happy to have you here, and thank you very much.
Thank you.